Suppose we have a real valued function of three variables, being x, y, and z, and a curve that's lying in a domain of f. So if we partition the curve into a finite number of segments, which can have a non-uniform arc length, so if we index the segments using index I, then each segment will have an arc length delta Si. And if we choose a point arbitrarily in each segment, so in segment I, we evaluate the function at the point with coordinates xi, yi, and zi, then we can write a similar form of the Riemann sum as we did for normal integrals, double integrals, and so on. So we have the sum from I equals 1 to the number of segments dividing the curve of the function evaluated at xi, yi, and zi, and that's multiplied by the arc length of segment I. So the value of the Riemann sum depends on the point we choose in each segment and the partition we use to segment this curve. So if the function is continuous, then the Riemann sums approach the same limiting value. So if we take the limit of the Riemann sum as the number of segments approach infinity, or the length of the largest segment approaches 0, then the limiting value is the integral of the function of x, y, and z over the length of the curve. And this is known as the line integral. Now suppose we parameterize this curve by taking a position vector from the origin to a point along the curve. Then we can write r as a function of the parameter t, and that's equal to the x-coordinate of the point on the curve as a function of t, which is the I component, plus the y-coordinate as a function of t, being the j component, and plus the z-coordinate as a function of t in the k direction. And now we can do a change of variables. So ds is ds dt, and take the parameterization between t equals a and b. So for example, we're parameterizing the curve between t equals a and t equals b. Then for a smooth curve over this interval, meaning that the velocity vector, being the tangent vector to the curve, and the first derivative of the position vector with respect to t, is continuous and never equal to the 0 vector, so we never get an undefined derivative, then ds dt, being the derivative of the arc length function along the curve with respect to the parameter t, is the magnitude of the velocity vector at t. And that's always positive. So remember that s of t is the arc length function and the directed distance from the base point that we select on the curve. So noting that in doing the change of variables, we're integrating over t instead. So therefore, we can make the substitution where f is a function of x, which is a function of t, and y is a function of t, and z is a function of t, and that's multiplied by the magnitude of the velocity and integrated over t from t equals a to t equals b. So therefore, we can essentially evaluate our integral of a function of three variables over the length of the curve as a line integral over t. So to evaluate the integral of a continuous function over a curve, all we need to do is find any smooth parameterization of the curve over the closed interval from t equals a to b, and we can evaluate the line integral over t. Suppose we have a piecewise smooth curve. So for example, the curve consisting of this red curve and this green curve connected at a point, or another smooth curve, such as a line, being connected at this point. So we generally have a finite number of smooth curves, being C1, C2, and so on, up to Cn. Then a line integral of a function of x, y, and z over the entire curve C can be evaluated piecewise over each individual segment. So we have the integral of our function over the red curve, which we'll call C1, plus the integral of the function over the length of the green curve, being C2, and so on, plus the integral of the function over the length of curve N. And in general, the line integral along a path joining two points is path dependent. So for example, if we evaluate the line integral over this piecewise smooth curve from point A to point B, and instead integrate our function over another path between these 2 points, then a line integral will give a different value, except in a few special cases, which we'll look at later on. Let's evaluate the integral of the given function over the union of the line segments L1, which is from the origin to the point with coordinates 1, 1 and 0. So our first line segment looks like this, and the line segment from 1, 1, 0 to 1, 1, 1. So this line segment looks like this. So therefore our line integral of our function over the length of the piecewise smooth line segment is equal to the integral of our function over line segment 1 plus the integral of the function over line segment 2. So what we do first is parameterize both line segments. So using the position vector, we can parameterize line segment 1 as t in the I direction plus t in the j direction. So at the origin, we have t equals 0, giving the point with coordinates 0, 0 and 0. And when t equals 1, we get the point with coordinates 1, 1 and 0. So that's our first line segment. And now we parameterize our second line segment. So in this case, the x and y coordinates do not change. So we have I plus j. And the z coordinate varies from 0 to 1. So we have plus t multiplied by k, where t varies from 0 to 1. And recall we can write our line integral over t as the integral from t equals a to t equals b. And we're integrating our function, which is t squared plus 2t minus 0, because there's no z coordinate, and that's multiplied by the magnitude of the velocity, which we obtain by differentiating the position vector. So we have v1 of t is equal to I plus j. So therefore the magnitude of v1 is the square root of 2. So we take that outside the integral because it's constant and integrate over t. And our integral over the second line segment is from t equals 0 to t equals 1. And here we have x equals 1, y equals 1, and z is equal to t. And if we differentiate this function, we get v2 is 0 plus 0 plus k. So therefore the magnitude of v2 is 1. So we multiply this by 1 and integrate over t. And now we can evaluate these integrals. So we have root 2 by t cubed on 3 plus 2t squared on 2, evaluated at 0 and 1, and plus 1 plus 2 is 3, so we get 3t minus t squared on 2, evaluated at t equals 0 and 1. So that gives root 2 by a third plus 1 plus 3 minus a half. So 1/3 plus 3/3 is 4/3. So we get 4 root 2 on 3. And 3 is 6 on 2 minus a half is 5 on 2. So that's the integral over our piecewise line segment being L1 union L2. Integrate the given function of x, y, and z over the path from the point at the origin to another point Q with coordinates 1, 1, and 2. And this path is given by the following curves. So for the first curve, we have x equals t and y equals t squared from t equals 0 to 1. So this here is a parabolic curve, because if we square the first equation, we get y equals x squared. So that curve in the xy plane looks something like this. And the other curve has a constant x coordinate of 1 and a constant y coordinate of 1, and z is equal to t. And t is between 0 and 2. So at t equals 0, this line has a base point of 1, 1, 0. And at t equals 2, the line segment finishes at point 1, 1, 2. So let's evaluate the line integral piecewise. And we first integrate our function over curve C1. So what we have is x is equal to t and y is equal to t squared. So t squared to the half is t, and z is equal to 0. And we multiply this by the magnitude of the velocity vector. So what we have is v of t, which is obtained by differentiating r of t. So we get I plus 2tj. So the magnitude of the velocity vector is the square root of 1 squared plus 2t squared, which is 1 plus 4t squared. Or 1 plus 4t squared to the half. And we integrate over t from t equals 0 to 1. And we add the integral over curve 2. So our function in this case is 1 plus 1 to the half, which is 1, minus a half z squared. So that will be minus a half t squared. And we multiply this by the magnitude of the velocity vector. So if we differentiate this function, we get v of t is 0 plus 0 plus k. So the magnitude of the velocity vector is 1 in this case. So we multiply by 1 and integrate over t from t equals 0 to t equals 2. And we can simplify this integral. So t plus t is 2t, and 1 plus 1 is 2. So we can evaluate the first integral by substitution. So we have u is 1 plus 4t squared. So du is 8t dt. And we can rewrite this integral. So we have 2t dt is du on 4, and we're integrating u to the half over u. So when t equals 0, u equals 1, and when t equals 1, u equals 5. So this integral evaluates to 1/4 by u to the 3 on 2 on 3 on 2, which is 2/3 u to the 3 on 2, evaluated at u equals 1 and 5. So if we factor out 2/3, we get 2 on 12, or 1 on 6, by 5 to the 3 on 2, minus 1. And then evaluating the second integral, we get 2t minus t cubed on 6, evaluated at t equals 0 and 2. So what we get is 4 minus 8 on 6, or 4 on 3, and 4 is 12 on 3, so this gives 8 on 3. So combining these results, we get 5 to the 3 on 2 on 6, minus 1 on 6, plus 8 on 3, and 8 on 3 is 16 on 6, so minus 1 plus 16 is 15 on 6. So we can write our final result as 1 on 6 by 5 to the 3 on 2 plus 15.